In this demo, we'll see how you can perform batch prediction on Vertex AI. Batch prediction is extremely valuable because it allows you to apply machine learning models to large data sets efficiently. Instead of processing individual data points or responding to individual prompts, as we've done so far, you can submit a batch of data to Gemini for prediction and you'll save time and computational resources. What we've been doing so far is online prediction with generative AI models. We'll now see a very simple example of batch prediction using the generative Gemini models that Google has to offer. I'll just give you a heads up that with batch prediction, you'll typically pass in, say, a large number of images and get information about those images in one go. I'm going to keep our batch prediction example very, very simple because we haven't worked with images and other documents yet using the Python SDK. I'm going to send a number of different prompts in a batch. In fact, we'll just send 2 prompts in a batch. We'll configure a batch job that will run and generate responses to those prompts. Now, this batch prediction demo has 2 parts. We'll first read from and write to Cloud Storage buckets, and then we'll read from and write to BigQuery. This demo will walk you through a very simple use case, but as you learn more and work with Vertex AI further, you should be able to expand this to more complex use cases later. On the Google Cloud Console, here I am on the All Products page. I'm going to head over to IAM and Admin to configure a service account. A service account on Google is a special type of account used by applications or virtual machines to interact with Google Cloud services securely without needing a human user. The service account provides authentication through key files or built-in credentials and can be assigned specific roles and permissions for fine-grained access control. Here in Identity and Access Management, let's head over to Service Accounts on the left, and here I'm going to create a new service account that will be used by my batch prediction job. Now, this service account that I'm about to create, I'm going to call it Vertex AI Batch SA, where SA stands for Service Account. This account will have access to Cloud Storage and BigQuery so that it can read data from these products and services and write data to them as well. This service account will need read-write access to both Cloud Storage and BigQuery on the Google Cloud, and it will also need some Vertex AI specific roles. So let's go ahead and add the roles that this service account needs. The first is Vertex AI user. The batch prediction job needs this role to have access to all resources in Vertex AI. The next role that I'm going to add is that of service account token creator. This will allow our batch prediction job to impersonate service accounts as needed, that it can run using the credentials of the service account. The next role that I add is going to be to access Cloud Storage buckets. So I'm going to make the service account a storage object admin. This will give the service account full read-write access to buckets and data in Cloud Storage. We are going to run a second batch job using the same service account to access BigQuery. So I'm going to add the BigQuery data viewer role as well. This will allow the application to query BigQuery tables. The next role that I add is BigQuery job user. This will give the service account access to run jobs on BigQuery. So it can run jobs to read from a table and write to another table. And the last role that I'll assign this service account is that of BigQuery admin. Allow it to administer all BigQuery resources and data. Now, these are necessary and sufficient to allow the batch prediction to do all of the operations that we'd like it to perform. Go ahead and click on Done. The service account that will act as the identity for our batch prediction job has been created. Go ahead and click through to the service account and let's generate a JSON key. This is the JSON key that our batch prediction job will use to run. So head over to the Keys tab, click on Add Key, click on Create New Key and download the JSON file to your local machine. So make sure you set up your service account correctly and download the JSON file. I'm going to call it service account key. It's going to be in my downloads folder. I'm going to move that JSON file into my current working directory. So my JSON file, which contains the service account key, is in the same folder as the batch prediction Python notebook. Now let's head back to the Google Cloud Console. And if you go to the main identity and access management page, you should find the service account that you've created listed there and whatever roles you've applied to the service account. Now, if this looks good, let's head over to Cloud Storage and create a bucket that will contain our batch prediction input file. So go to View All Products and go to Cloud Storage. Cloud storage buckets give you object storage on the Google Cloud. This is elastic storage that grows as you add more data. Now, here on Cloud Storage, let's head over to buckets and create a new bucket. Click on the Create option. Bucket names have to be globally unique, that is, unique across the entire Google Cloud ecosystem. So maybe prefix your bucket with the prefix of your organization to ensure that they are indeed unique. I've called mine Looney LLM bucket. Next, you specify where you want your data to be stored. Multi-regional buckets give you the highest redundancy. Dual regional buckets will store your data redundantly in two regions. A regional bucket will store your data within a single region. That's totally acceptable for us. Let's go ahead and pick a regional bucket. In order to minimize transfer charges, it's best to keep your bucket in the same region where you're running your Vertex AI resources. We are always using Vertex AI APIs from US Central 1 in Iowa, so that's the region I've picked for my bucket. Select the storage class for your bucket based on how often you plan to access the data stored in the bucket. Standard storage is best when you plan to access the data frequently, and that's what I've picked. Next, you'll be asked to specify how you'd like to control access to the objects in your bucket. Now here you can go with any option. I'm going to uncheck Enforce Public Access Prevention on this bucket. Maybe some of my objects will be publicly available, and I'm going to set Access Control to be fine-grained. This will allow me to assign permissions at a granular level to individual objects in my bucket. Now it doesn't matter what options you pick here for the batch prediction job. Now on Google Cloud Storage buckets, the soft delete policy is turned on by default. This means buckets will retain content in a deleted state, potentially resulting in significant storage costs. In order to optimize your storage costs, it's probably better to turn this off, and that's what I'm going to do. This is what Google recommends for batch prediction. Now you can leave the data encryption options to their default values. Data will be encrypted using the Google managed encryption key. Finally, let's go ahead and create this bucket. This bucket will contain the source for our batch prediction job, and the results of batch prediction will be written out to the same bucket. This is the Looney LLM bucket that's currently empty. Let's create a new folder containing our input for the batch job. I've called the folder batch input. This is the folder to which I'll upload the JSON-L file containing our batch prediction inputs. Now I'm going to create yet another folder here that will contain the output of our batch prediction job, and I'm going to call this folder batch output. The batch prediction job that we'll run will write to this batch output folder. At this point, we're all set up to run our batch prediction job. So let's head over to our Python notebook. I'm going to be using a few different libraries here. I'm going to be displaying data in a data frame using pandas. So I pip install that within my virtual environment. I also need the db types library to allow me to work with BigQuery data types. So I go ahead and install this library as well. Next, I'm going to go ahead and set up the imports that we need to run our batch prediction jobs. I'll explain these classes as and when we use them. Now, the batch prediction job will run using the credentials that we've configured in our local environment. By default, we have our logged in users credentials in the local environment. That's what the application default credentials will pick up. Now, instead of running the batch prediction job using our logged in users credentials, I'm going to configure this environment variable called Google Application Credentials and point it to the credentials of the service account that we've just created. Google Client SDKs make use of something known as Application Default Credentials to authenticate themselves to Google services. Application Default Credentials looks in various places to find the right credentials to connect to the Google Cloud. And if you have this environment variable configured, these are the credentials that Application Default Credentials will pick up. Now, why do I set up this service account in this environment variable? If you're running your batch prediction job in production, You do not want it using your logged in user's account. You want it using a service account with only those permissions that the batch prediction job needs to perform its tasks. In the learning phase, for the remaining demos, I use the logged in user's account. But in this demo, I wanted to give you a little taste of how you set up your batch prediction job in production by using a service account for authentication. Let's initialize Vertex AI as usual with our project and location. Next, I specify the model that I'm going to use. Let's use the Gemini 1.5 Flash 002 model. The input to our batch prediction job is in the form of a JSON-L file. This is a JSON lines file. And here is what my file looks like. Every line in this file is a separate request that we'll make to the generative model. Notice within request, we have the contents. Within contents, we have the role, that is the user role, that's the user prompt that we are sending the model. And the text contains the actual prompt itself. Now here, I'm performing batch prediction for these very simple prompts. But in the real world, you might want to process multiple documents and images in one go with batch prediction. All you'll have to change is this JSON-L file. Google's documentation will show you how you can update the structure of this JSON-L file to include documents and images in your bucket. We'll keep our focus on how we actually run batch prediction. Let's head over to the batch input folder in our cloud storage bucket, and I'm going to upload this input JSON-L file from my local machine to this folder in my bucket. We need the URI of this input file to our batch prediction job. So click through to the file, and here you'll find the gsutil URI. Go ahead and copy this over. Notice that it starts with the prefix gs://. The output of the batch prediction job is going to be placed in this batch output folder. Let's click through and let me show you that this folder is currently empty to start off with. Back to our notebook, let's set up the input and the output. The input data is the URI of the JSON-L file that we uploaded to the batch input folder. And the output is the gsutil URI for the batch output folder. That is the bucket URI. Now let's submit a batch prediction job to Vertex AI. Call batch prediction job.submit, specify the model ID, specify the path to the input dataset, and specify the output URI prefix. This is the bucket URI that will contain the actual predicted output. We have a reference to the batch job in the batch prediction job variable. Go ahead and submit this, and notice the job has been created. If you click through to the link that you see here at the output, this will take you to the batch prediction jobs page where you can monitor the progress of the job. Observe that the status of the job is currently running. Notice that we have a link to view the logs for this job. So if the job fails for some reason, you can view the logs to debug. Notice the import location where our input data is placed. Now, if you go back to the previous page, this will take you to the main page for the batch predictions service. And you can see our job is currently running. You can use the batch prediction job variable to get details about the job, the resource name, the model name, and the name of the current state of the job. Here, it says job state pending. It hasn't been updated. Our job is currently running. In order to access the latest state of the job, call batch prediction job.list and print out the job name, the job state, and the job model. This will give you a list of all batch prediction jobs running. We have just one, so we get only the information for that job. You can see the job state here is currently running, and we are using the Gemini 1.5 Flash model. You can use a while loop to continuously monitor the status of a batch job in your notebook. So while not batch prediction job has ended, I sleep for 5 seconds within the while loop so that we are not constantly hitting the API. And then I call batch prediction job.refresh to get the latest status of the job, and I print out the job's state. Once we get out of the while loop, I check whether the batch prediction job has succeeded. If yes, I print out job completed successfully. Otherwise, I print out job failed with error. I'm going to go ahead and run this. It took about 2 to 3 minutes for my batch prediction job to run through, but finally I saw job completed successfully, which means I should be able to access the prediction results in cloud storage. Let's go to the batch prediction job. You can see that it has completed successfully. And if you click through and look at the details, you can see that it ran through in about 2 minutes and 56 seconds. Let's confirm the output location where the predictions of this batch job are available. And you can see it's the batch output folder in our Looney LLM bucket. We can programmatically verify whether this result is available here in this bucket. Here on line 4, I instantiate a Google Cloud Storage client, and on line 6, I get a reference to the Looney LLM bucket. And then I call bucket.list blobs and specify the directory path batch output to see what blobs are available in that bucket. I then run a for loop iterating over each blob. Now our predicted output will be stored in a JSON-L file. So on line 2, I check whether the blob name ends with .jsonl, and then I download the blob as a JSON-L string on line 4. I then convert the contents of the JSON-L file to Python dictionaries on line 8. And on lines 10 through 16, I decode each JSON object in the JSON-L file, and I print out the contents of the JSON object. And here are the JSON object's contents. These contain the predictions for the 2 prompts that we sent the Gemini model. Now, there's a lot of stuff here. It's hard to see what's going on. So let's take a look at the dictionary that we had parsed from the JSON-L file. If you look at dictionaries, you can see that there are 2 results. Here is the first response about artificial intelligence. The text field within content contains the response. And if you scroll further down, you'll see the second response. The text field within content talks about machine learning. We've successfully used batch prediction to get the responses from our 2 prompts. I'll parse out and access the first text response. This is in the markdown format. So I'm going to use the markdown object in order to display it in a nice manner. So here is the first response about artificial intelligence. The response is very long and detailed, and that's why the response seemed so huge. Let's parse out the second response as well to verify we've got it correctly. Here is the second response, and I'm printing it out in the markdown format. And this is the response to the machine learning question. Now that we've successfully performed batch prediction for our simple prompts, we can go ahead and delete the batch prediction job. Call batch prediction job.delete, and it should get rid of that job from our account. Now, if you head over to the Google Cloud Console UI and hit refresh, the job should no longer be listed here. This was batch prediction with Google Cloud Storage buckets as the source and destination. Next, we'll do batch prediction with BigQuery as the source and destination. Let's say rather than cloud storage, your data is stored in BigQuery. BigQuery is Google's data warehouse where you can store structured data in the form of tables. At the time of this recording, batch prediction works with cloud storage as a source, and it also works with BigQuery as a source. Here I am in the View All Products page, and I'm going to scroll down and access the BigQuery console in my project. BigQuery is a serverless data warehouse, which makes it very easy for you to store, query, and analyze your data. Notice our project is present here on the left. Under this project, at this point in time, we have no BigQuery datasets or tables configured. A BigQuery dataset is a top-level container within which we'll create and set up all of our data resources. Now let's head back to our notebook. Remember that this notebook is currently running using the identity of the service account that we had configured in the Google Application Credentials environment variable. While setting up the service account, we had assigned it the BigQuery admin role so that it could create and work with datasets and tables in BigQuery. And that's exactly what we're doing here in this code. On line 3, I instantiate a BigQuery client for our project. On lines 5 and 6, I set up the dataset that I'm going to create within our project. The dataset ID is Gen AI batch prediction, and the dataset reference is the full path to the dataset, that is project ID dot dataset ID. On lines 8 and 9, we initialize the dataset and its location. We want the dataset to be in the same location where we are running our Vertex AI APIs, US Central 1. And finally, on line 11, we create the dataset. Exists OK equal to true will not throw an error if the dataset already exists. Go ahead and run this, and it seems like the dataset was successfully created. If you head back to the BigQuery console and hit refresh on your project, you'll find that the new dataset is present there. We now need to create a table within this dataset that will store our source data. On lines 3 and 4, we set up the table ID. It's called batch input data. That's the name of the table. And the reference to the table is the full path to the table. Project ID dot dataset ID dot table ID. Now this table is going to have 3 columns or 3 fields. That's the schema on lines 6 through 10. The fields are request, user ID, and timestamp. The request will hold the actual contents of the request for batch prediction. On lines 12 and 14, we set up and create this BigQuery table. Let's run this and let's head over to the BigQuery console to verify that the table has been created. If you refresh the contents of the dataset, you should find the newly created batch input data table in there. And if you select this table, you'll be able to see the schema of the table. And if you head over to preview, you'll see that the table is currently empty. Back to our notebook, let's insert some data into this table. Here are the rows to insert in the form of a list of dictionaries. There are a total of 3 requests that we'll make as a part of the batch prediction. The first one is on lines 2 through 18. The request field contains the actual JSON of the request. The JSON has the contents field, which contains the actual prompt that we're going to send the model. The first prompt here on line 8 says, what are the benefits of meditation? Next, on lines 12 through 14, we have the system instructions. And here the system instructions say, you are a wellness coach. In addition to the request, we also have the user ID and the timestamp. Request, user ID, and timestamp are the 3 fields in our BigQuery table. Now you can see that I have 2 other requests defined in the same way. These are the 3 rows that we'll insert into the BigQuery table. On line 55, I perform the insert operation by calling insert rows JSON, and I print out whether the insert was successful or not. Let's go ahead and run this, and it seems like the rows were inserted successfully, and we can definitely verify this on the BigQuery console. Refresh this preview pane and you can see the 3 records here. These are the 3 records that we'll use for batch prediction. If you look at the request column here, you can see that the structure is in the JSON-L format. This is the same format that we used in batch prediction with Cloud Storage. That was a JSON-L file. This is just JSON-L within a BigQuery table. It's now time for us to set up the batch prediction job. Here is a reference to the input data that the job will use. Make sure you specify the full path to the BigQuery table that contains the data. That's BQ : / the project ID dot dataset ID dot table ID. Let's run a SQL query on the input data and view the results here as a data frame. For this, we'll need the db_dtypes library. So go ahead and import that. Now we'll run a SQL query on our BigQuery table. For that, we need the BQ table ID. That's everything in the input data string except for the prefix. So we replace the prefix with the empty string. That will give us just the table ID. The SQL query that I run is a simple select star from the BigQuery table. I call BQ client.query, pass in the SQL, and I display the results as a data frame. And these are the contents of the data frame. You can ignore that warning there. Vertex AI wasn't able to find the BigQuery storage module, so it just fell back to using the REST endpoint to retrieve the data. Now let's set up the path to the output table where the prediction results will be stored. On lines 5 and 6, we set up the prediction table ID. Notice the prediction table ID has the prefix prediction_result and the current timestamp as the suffix. Then on line 8, we set up the BQ output URI. This is the full path to the prediction table. It starts with the BQ : / prefix. Then we have project ID dot dataset ID dot BigQuery table ID. On lines 10 through 12, we get a reference to the same dataset that we've been using so far, our Gen AI dataset. On line 14, I create this dataset. It will be created if it doesn't already exist, but since it does, there'll be no action performed. And then I print out created the BigQuery dataset and I print out the output URI. Pay close attention to the output URI, that is the prediction result table with the current timestamp. Note that we haven't created this table yet. That will be done by the batch prediction job. We are now ready to create our batch prediction job called batch prediction job.submit. The source model is the same Gemini model that we've been using. Input data set is input data, that is a reference to the batch input data table, and the output URI prefix is the BQ output URI, that is the prediction result table that we just set up a reference to. This batch prediction job will create the table and populate it with results. Let's go ahead and run this. And here you can see the job has been created successfully. Let's open up the jobs page and you can see that it's currently running. Let's go to the main page and the job seems to be running well so far. Let's go back to our notebook and view the status of the job. I'll print out the resource name, model name, and the status name. The job state is stale. It still says pending, though our job is currently running. Let's go ahead and list out all of the batch prediction jobs available and their current state. And you can see that the current job state is running. Now, let's get the latest state of the job by querying the API. While not batch prediction job dot has ended, we'll query the job and print out its state. And once it completes, we'll print out whether the job was a success or failure. It seems like the job has completed successfully. Just a reminder that this batch prediction job executed using the credentials that we had configured in this notebook. That is the credentials of the service account we had set up earlier. The output location will tell us where the results of this job have been stored. And you can see that it's the prediction result table that we had configured earlier. Let's head over to BigQuery and view the results. Refresh the contents of this dataset and you'll find the new table with the prediction result. There is our prediction result table. Let's click through and view the data in this table. You can see the schema of the prediction result, and under preview, you'll be able to see the actual contents of the result. The prediction result holds the request and the response. And the response is where you get the output of the generative AI model. Let me make this as wide as possible so you can see things clearly. Here in the response field, you'll see the response to our queries. The first response is about meditation because that's the question that we had asked. We had asked the model to play the role of a wellness coach. The second response is a joke about a cat. We've successfully run a batch prediction job using BigQuery as the source and the destination. I'm going to go ahead and delete this job so that I clean up the resources that I have created. Once you've done this, let's head over to the batch predictions page and hit refresh, and you can see the job no longer appears here. In this demo, we'll work with the image understanding functionality that Gemini models offer. Gemini can understand the contents of the images that you include in your request and can answer questions about those images. Because we are working with images, I'll install the Pillow library that will allow us to display images on screen. Now, once this pip install is complete, let's do our usual setup. We'll set up the imports for this particular demo. And once we have the imports, we'll initialize the Vertex AI client with the project ID and location that we're using for Vertex AI services. Now you can pick the latest model that Google has to offer for image understanding. I've gone with a fairly recent model at the time of this recording, Gemini 1.5 Flash 002. Instantiate the generative model. Because we are working with images and images often tend to be large, I'm going to upload the images to a cloud storage bucket and we'll reference those images from the cloud storage bucket. Here I am in the Looney LLM bucket that we have created earlier. Here I'm going to create a new folder called images and I'm going to upload all of the images that I use in this demo to this images folder. Having images in a cloud storage bucket makes it very easy for you to actually set up your requests. You can simply reference the images stored in cloud storage. I'm going to upload all files in my local machine. These are all of the images that we'll use in this demo. These are present in an images subfolder under my current working directory. Now that these images are available on cloud storage, let's work with these images in our notebook. Now the bucket name is the Looney LLM bucket. You should update it to whatever bucket you're using. Now the first image that I'm going to ask the model to interpret is this dogs playing image. All of the images that I use are freely available on pexels.com. for regular and commercial use. We've seen in the past how you can pass the text contents of your prompt in a part object. Similarly, you can reference images from cloud storage and set those up in a part object. On line 1, part from URI will access our dogs playing.jpg image from our cloud storage bucket and generate a part object to represent this image. On lines 3 through 6, we call model.generateContent and we pass in 2 bits of content in the form of a Python list. The first is a reference to the image file, that's the part object, and the second is our prompt. Could you explain what's going on in this image? And here is what the model has to say. It has clearly identified 2 golden retrievers playing tug of war in an outdoors green lawn setting. Just like with regular prompts, image understanding responses can be streamed as well. Here on lines 1 through 4, I call model.generateContent with the same prompt as before, except I've set stream is equal to true. And then on lines 8 through 11, I do something nifty with the streaming. I iterate over the responses in the response stream. I print out the response chunks on line 11, but I'm also computing the complete text on line 9. Now remember, the response is in Markdown. So after we've streamed out the response, I clear the output and I display the formatted Markdown result. So we get a nice display in the HTML format. When I run this, you'll first see the stream contents written out that is not formatted as HTML, and finally the end result is in the HTML format. You can configure the parameters of the response when you're working with images as well. Now I'm going to set temperature to a lower value, 0.7, max tokens 300, top P is 0.9, top K will not be considered by this model, but I've set it to 40. Now let's stream a response using this generation config. When I call model.generateContent, I pass in a number of input arguments. On line 2, we have contents, that's just a Python list. This contains the image file in the cloud storage bucket and the prompt. On line 3, I set stream is equal to true, and on line 4, I specify the generation config. And on lines 7 through 15, I print out the streaming result. And here is a story based on the image. You can see that it's a pretty interesting story with a lot of detail. If you look at the end, you can see the response is cut off or truncated. That's because of our token limit. Let's try the story again with a different generation config. I'm going to set temperature to a high value of 2, which means that the response from the model should be more creative, more diverse. I've also set max output tokens to 500 so the response can be longer. Top P to 1, that's the maximum possible value. Top K anyway will be ignored by this model. Now let's go ahead and send the same prompt once again. We'll generate a story. And here you can see that the story is longer and much more detailed and much more vivid. In fact, it's a little overly dramatic. You should be aware that if you set a very high temperature, the results may not be always what you expect. You can see as you read some of these sentences, some of them seem rather awkwardly constructed. That can happen with a high value of temperature. Let's work with another image. Let me show you that image first before we use it in a prompt. This is a dog playing with a ball on some green grass. Now let's look at another image. This is a dog playing with a ring. I'll show you a third image that I'm going to use, and this image has a dog playing with his toys. Gemini models allow you to pass in multiple images at the input. Now I use part.fromURI to load in part objects for each of the 3 images that we looked at. I have these stored in image file 1, image file 2, and image file 3. Please observe on lines 3, 8, and 13, I set the MIME type of each image to be the right type, either PNG or JPEG. I'm going to pass in multiple images to the model and ask it a more complex question. I call model.generateContent, and in the contents, I have a list. The first 3 elements in the list are the part objects corresponding to the 3 image files, and then the 4th element is the prompt. What's common across these images and what is different. And I'll print out the response in the HTML format. And here you can see that the model has analyzed this perfectly. What's common are the dogs and the playful context, and what's different, breed of dog, the activity, the setting, and the age and size of the dogs. Gemini models are very powerful and they can work with images in many creative ways. Now, here I have two images that I downloaded from this URL that you see here on screen. These are the original source of the images. Now, these two images show similar context, but there are a few differences between the two images. This is a game that you might have played when you were younger, spotting the difference between two images. Now, this is exactly what I'm going to ask the Gemini model to do, spot the difference. Let's go back to our notebook and see how well the model performs. On lines 1 through 8, I've set up part objects referencing those two images. On lines 10 through 16, I call model.generate content and I pass in the two images, and my prompt says spot 10 differences and 10 similarities between the two images. The model will have to do a lot more reasoning to respond to this. Let's see what the model has to say. And if you look at the differences section, you can see that it has spotted many differences. It doesn't talk about the position of the basketball though in the hoop. That one it has missed. And if you look at the similarity, you can see the model has got it spot on here. The image understanding capability of Gemini models can be useful for your technical tasks as well. Here is a diagram of retrieval augmented generation. We'll implement this AI technique later on in this course. This technique combines information retrieval with text generation, which allows a model to fetch relevant external data to enhance the accuracy and context of its responses. This diagram that you see here explains how a RAG system functions, the components of the RAG system, and how they interact with one another. You can feed this image into the model and have it teach you about how a RAG system functions. On lines 1 through 4, I set up a reference to the RAG diagram. This is a part object. And on lines 6 through 15, I pass in this image file and I ask the model a question about RAGs. I want to know how RAGs work, the individual steps, and at what step we use the knowledge base. Let's see what the model has to say. And it does a perfect job. It has correctly explained every step to me. And if you look at the bottom, you see that it correctly tells us that the knowledge base is utilized in step 3. Let's look at one last image before we move on to other topics. Here is an image of a microwave, and I'm curious about how this microwave works, how I would interact with the microwave. I'm going to ask Gemini this question. I access my image file on top, I call model.generate content, and I ask a specific question. How can I configure the temperature of this microwave? Please give me instructions on which button I should press. Let's see what the model has to say, and it says press the number buttons. And because it found a temperature button as well, it tells me that it may be necessary to press this button after entering the numerical temperature. I felt this was a really well reasoned response. As you already know, Gemini models are multimodal. That is, they can work with different kinds of input modes. Text, we've already seen they work with images, they work with videos and audio files as well. In this demo, we'll see how you can include video files in your request and ask the model questions about what's in the video. You'll see that the model is pretty good about video interpretation. Let's get started the usual way. We'll import all of the classes and libraries that we need, and we'll call vertexai.init to initialize the Python client library with our project and location. At the time of this recording, there are 3 Gemini models that support video understanding. Gemini 1.5 Flash, which is what we're using, Gemini 1.5 Pro, and Gemini 1.0 Pro Vision. The 1.5 models support video lengths up to 60 minutes without audio and up to 50 minutes with audio. They also support up to 10 videos in a prompt. The Pro Vision model, the 1.0 version, can only process videos of up to 2 minutes and can accept just one video per prompt. Now let's instantiate the 1.5 Flash model. And since video sizes tend to be fairly large, let's upload the videos that we're going to process to our Looney LLM bucket. I'm going to create a new folder here called videos, and I'm going to upload all of the videos in this demo to this folder. Just click through to this folder and you can simply drag the videos to this folder, or you can click on this upload button and upload files from your local machine. These video files that you see in the video subfolder should be included as a part of the assets of this course. Select all of them and go ahead and upload them. All of these videos are either from pexels.com, or the last videos that you see there, the one with audio file. Well, that's a video of mine from another course available on Skillsoft Percipio. I'll show you what these videos contain as we use them in our prompts. Let's start with the very first video. This has no audio and this just shows some waves at sunset. Our very first prompt is going to be about this particular video. Now I've set the bucket name to Looney LLM bucket. Let's set up the video file as a part object. I use part.fromURI. The URI is the gsutil URI pointing to sunsetwaves.mp4. Gemini models can support a variety of video formats: MP4s, MPEGs, WebMs, WMVs, and so on. Now that we have this video file, let's set up our prompt. The prompt is fairly simple. Can you describe the key scenes in the video? And the contents include the video file and our prompt. We call visionmodel.generateContent, and let's look at the response, and it correctly describes the sunset over a calm ocean. There's a lot of detail about the colors and textures in the scene. For the very same sunset waves video file, I'm going to set up a different prompt. I'm curious about what emotions are conveyed through the video, and I ask for a detailed analysis of the changes in mood, pacing, and visual elements. Let's go ahead and send this prompt along with the video to the model. On line 3, I call visionmodel.generateContent, pass in the contents, and I've set stream equal to true. And on lines 5 through 13, I print out the chunks in the streaming response and then the final result using the markdown class so that we get the result in HTML. And you can see a detailed analysis of that little video snippet that we had. When you're working with videos, you can configure the generation config for the model's response as well. Here I've set temperature to 1.5, max output tokens to 300, top K, well, the model will ignore, but I've set that to 40, top P is 0.9. In addition, I've specified a presence penalty and a frequency penalty. Non-zero values for these penalties penalize the model for generating repetitive text in its response. So the model will be less likely to repeat itself when you have these penalties. Let's use this generation config with the same prompt as before and get the response from the model. Because of our token limit, the response is shorter and conveys less detail, but thanks to our temperature parameter, the description is very, very vivid. The next video that I'm going to have the model analyze is the blooming flower video. Now I'm just going to play this video. It's a very short one, just about 15 seconds or so, and all it does is show a flower blooming and there's absolutely no audio. The basic query with a video is, of course, to explain what that video does or describe the video, but here we look at a different query. I'm going to set up part objects for two video files, Sunset Waves MP4 and Blooming Flower MP4. Both of these are in our cloud storage bucket. The Gemini 1.5 model that we are working with supports multiple videos in a single prompt. My prompt here is different. I've asked the model to generate 10 Twitter, now X hashtags for each of these videos. The contents include the two videos and our prompt, and I call visionmodel.generateContent. And here you can see sunset at the beach. There are 10 hashtags there. And then we have close up of a rose and we have 10 hashtags for those as well. I'm going to play another video here and I'm going to ask more complex questions of the model. Let's go ahead and play this video. There is no audio at all, but you can see this video is about an audience who's happy with what they see and hear on stage. There are 7 people in the video. There are 2 men, 4 women, and a third unknown person at the very right. Let's reference the video in our cloud storage bucket as a part object, and let's send a prompt to our model. Can you tell me what people are doing in this video? That's my prompt. Call visionmodel.generateContent and pass in the video and the prompt. Let's see what the model has to say. and you can see it's a group of people sitting in chairs and clapping. And it has deduced that they are in a presentation, meeting, or performance. Let's get the model to interpret in a little more detail. Could you count the number of people and describe them in detail? This is my new prompt for the same video, and the model gives me a lot of information. But I think because of the panning of the video, the model gets some things wrong. It suggests that there are 8 people visible in the video. I looked carefully and there were exactly 7. If you look at the descriptions, it got the descriptions for the most part correct. It identified the woman with dreadlocks, it identified the man with glasses and a beard. Now I'm going to play the very last video. This is a technical video which talks about the TensorFlow framework for machine learning. This is a video from another Skillsoft course of mine. I won't play the whole video, just a very small snippet. In this learning path, we are going to be building some natural language processing models using deep learning. And the framework that we are going to be working with is TensorFlow using the Keras API. So let's understand what TensorFlow and Keras support. This is a very technical video that introduces TensorFlow and Keras. Let's reference this video file as a part object, and I have some detailed questions of this video to ask of the model. Describe the key moments and important statements. Who is the target audience? What prerequisites will they need to have? As a matter of curiosity, what accent does the speaker speak in? I'd like to be sure that the model has listened to the audio and has picked up my accent. Let's go ahead and submit this prompt to the model and see what it has to say. Now, this video is about 9 minutes long. You can see that it gives me minute by minute key moments and statements. And at the very bottom, it has correctly identified that the speaker seems to have an Indian accent. Now, the Gemini 1.0 Pro Vision model is an older model and it can only parse about 2 minutes of video. This is also a model that ignores any audio that is present in the video. Now, let's use this model, the Gemini 1 model, the Pro Vision model, and pass in the same prompt as before. You'll see from the response that the model has just watched the first 2 minutes of the video and then it just extrapolates from there. And you can see at the very bottom it says the speaker has an American accent. It hasn't actually heard me, but it still gives a response. These models are prone to errors. This is something that you need to keep in mind. Gemini models can handle audio input as well. And in this demo, we'll see how you can work with audio input in your prompts to Gemini models. Just a heads up that most audio files in this demo are AI generated. There is one audio file that I downloaded from a specific source. I'll mention that source when we come to working with that audio file. Go ahead and import all of the classes that you need. You can see the classes here. And I'm going to initialize the Vertex AI client as usual. Now, let's use the Gemini 1.5/002 model for this demo. If there is a more recent model available when you're watching this course, you could definitely try that out. The easiest way to pass audio files to a Gemini model is to upload those to a cloud storage bucket. Here in my bucket, I'm going to create a folder called audio, and I'm going to upload some audio files that I have on my local machine to this folder. You already know how to do this. Let's just see the audio files. Now, these audio files you can see are a mix of WAV files and MP3 files. Most of these files are quite small, containing under a minute of audio. But the 4065.mp3 file, that's a large one. Now, let's start with the very first, the forest mp3 file, and I'm going to play the contents of this audio file. I'll just play a snippet and not the entire contents. You'll get the picture though.
A forest is a vast, natural area covered predominantly with trees and other vegetation, forming an essential ecosystem for countless species of plants, animals, and microorganisms.
This was the voice of a female speaking English with an American accent. Let's set the bucket name to Looney LLM bucket. That's where our audio files are. Next, I'll set up the prompt and the part object for this audio file. On line 5, I have the gsutil URI, that is the Google Cloud Storage URI to this audio file. On line 7, I use part.from URI to get the part object referencing this audio. Notice I specify the MIME type as audio/MPEG. The MP3 format for audio is related to the MPEG format for video, so this MIME type should work fine. The contents is just a list which contains the audio file as well as my prompt. My prompt simply asks the model to summarize what is said in this audio in one sentence. I then call model.generateContent. Let's take a look at the response. The response contains the metadata as well as the text. Let's just look at the response text because that's what we're interested in. And here you can see a summary of what was in the audio in a single sentence. My previous prompt was to simply summarize the audio. Here I want a transcription, so my prompt changes. Please convert exactly what is said in this audio to text. This is essentially speech to text. Now the code on lines 5 through 11, that's familiar to you. The one difference here is that I've set stream equal to true, and on lines 13 through 19, I parse and display the streaming response. This will give me the transcription of the complete audio. You can see that the audio is about a minute, minute and a half, and earlier we got a one sentence summary. This is the complete text. The Gemini model did fairly well with that American accented English. Let's try English with a South African accent. I'm going to go ahead and play a small snippet of this audio.
The blacksmith tree wishes, a tale of wisdom and prosperity, en 'n kind verlaag genest het between rolling hills, deur hulle wet of nimble blacksmith name Thomas. Known for his exceptional craftsmanship, Thomas forget tools and horses for his fellow villagers.
I'm not familiar with this accent, so I find this hard to understand. This is the audio that we're going to send our model. My prompt here is a little different. I say, can you transcribe the audio and include timestamps for each sentence or phrase? And I also give the model a little hint. The speaker has a South African accent. The one thing that's different in the rest of the code here is on line 13. Notice that in the generation config I pass to the model, I set audio timestamp to true. This is what will allow the model to generate timestamps. And here, if you look at the response text, observe that we have the text and the timestamp at which that particular text was spoken. This is actually much easier to see when you print out just the response text. You get the timestamps, you can see the second base timestamps on the left, and then you get the sentences that were spoken in the audio. Now the transcription isn't that great. At 24 seconds, there is a mention of a weary traveler which does not appear again. And at 28 seconds, there is a peculiar liar. I'm not really sure what that refers to. Let's try with the same South African accented English once again, but I'm going to mislead the model. My change is in the prompt. I tell the model this is spoken in American accented English. Let me print out the model's response text and let's see how the transcription comes out with our misleading the model. Now the transcription is not as good as before. We get less fine-grained timestamps, and at 24 seconds, there is a pretty nonsensical sentence. In trickery, a bait sent to the core to test in, it tweaked the rumor to clean. I'm not really sure what the model was trying to get at here. Let's try English with a different accent. This is Nigerian accented English. This is a WAV file, and I'm just going to go ahead and play a snippet of this audio.
The 90s music scene was a melting pot of genres that defined a generation. Grunge exploded with bands like Nirvana and Pearl Jam, bringing raw emotion and rebellion.
Let's now question the model about this particular audio file. My prompt is different here. Can you identify the accent of the speaker? This is what I asked the model. Another change on line 6, notice when I create a part object using this audio file, the MIME type is audio/wave because this is a WAV file. I still have the generation config with the audio timestamp. I don't need that. Let's see what the model has to say, and the model says the speaker has a British accent. The way the model hears the Nigerian accent, I guess it's closest to the British accent. That's why it gives me this answer. This answer is definitely wrong, but I guess it's close enough. The model understands a variety of different languages as well. I have some content here in Danish. I'll just play it out to you, and then we'll use it in a prompt to the model.
Mode i 90'erne var en dristig blanding af grunge, glamour og afslappet elegance. Flannelskjorter, slitter jeans og Doc Martens blev ikoniske takket være grungebevægelsen ledet af Nirvana.
You could have asked the model to transcribe this, but I'm interested in what language the user is speaking in. That's my question to the model. and the model correctly identifies that the speaker is speaking in Danish. So far, we've given the model tiny snippets of audio. The model really hasn't been challenged much. That's going to change here with this 4065.mp3 file. This file is 30 minutes long. This file, not only is it long, but it contains a back and forth conversation. Here is the original source of this file. This is the URL where I downloaded this file from. I'll just play a small snippet of this, enough for you to know that there are two speakers involved.
Okay, how are you?
Oh, pretty good. Strange deal. What's that all about?
Well, I came across, I'm on a computer mailing list on my email.
Now we're going to ask the Gemini model to analyze this longer and more complex audio with multiple speakers. My first prompt here asks the model to analyze the sentiment of the conversation in this audio and classify into very negative, negative, neutral, positive, or very positive. The rest of the code is basically boilerplate code you've seen before. The overall sentiment is positive. You can see that it's not very positive because there are moments of negativity, discussion of deaths in the family, job security, health concerns. But the conversation overall is positive and optimistic. Now, for the same audio, here is a different prompt. There are two speakers, a woman called Bella and a man called Joseph. I want the model to transcribe this as a conversation between Bella and Joseph. I'd like any extraneous noises or sounds to be included as well. I've given a sample on line 6 and 7, so they should be Joseph and whatever he said, Bella and whatever she said. Now, the model took about a minute or two to respond to this. It had to parse the 30-minute audio after all. And here is the conversation between Bella and Joseph. Now, it's not caught everything perfectly because the audio was kind of indistinct in points, but overall it has captured the essence of what Bella and Joseph were talking about. Here is another question I had about the same audio. I'm curious about the tone that the speakers use. Are they friendly, angry, sarcastic, formal, or is there some other way to describe their manner? Let's see what the model has to say, and the model seems to indicate that the speakers are conversing in a friendly and informal tone. Now, I've heard this audio through and I did get the same feeling. They have a warm conversation. Next, I'm going to ask the model to deduce the relationship between the two speakers. Are they friends? Are they family members? Are they colleagues? Or do they have any other kind of relationship? Let's see what the model says to this particular prompt. Now, the model seems to think the two speakers are friends, and based on their conversation, they're also likely colleagues in the field of linguistics. The model correctly identifies that their conversation is mostly around professional lives and mutual friends, so it's a long-standing friendship stemming from shared professional backgrounds. Here is one last question I have for the model. I want the model to analyze this audio and describe what they're talking about with just 5-10 key takeaways. So kind of summary of what the speakers are discussing. And here are the bullet points of the various topics that the speakers discuss. You can include documents as a part of your request to Gemini models and ask Gemini to perform tasks that involve understanding the contents of the included documents. At the time of this recording, the models that support document understanding include Gemini 1.5 Flash and Gemini 1.5 Pro. A single PDF can include a maximum of 1,000 pages, and the maximum PDF file size is 50 MB. The Gemini 1.0 Pro Vision model also supports PDFs, but it can only support PDFs with a maximum of 16 pages, and the maximum PDF file size is 50 MB. Let's get set up with this demo as usual. We'll set up the imports that we need for this demo, and we'll call vertexai.init to init the client SDKs with the right project and the location where we use the Vertex AI APIs. Now, I'm using the latest version of the Gemini 1.5 Flash model. You can choose a more recent model if one is available to you when you're actually doing this course. Now, let's go ahead and upload the PDFs that we're going to be working with to a cloud storage bucket. I'll create a new folder here. You know how to do this, so I've just created the folder. The folder is called Documents, and I'm now going to upload the files to this folder. You can see all of the different kinds of files that I have uploaded. PDF files. I've also included a single text file. The first document that we'll look at, that is document 1 PDF, let me quickly show you the contents of this document. As you can see, this is a scientific research paper that I downloaded from archive.org. This paper tries to gauge student sentiment on mental health support in colleges using LLMs. Now, this is clearly a large and complex paper. Let's see if Gemini can help us understand this paper and summarize it. That's my first prompt. Summarize the main parts of this document clearly and briefly. The PDF file has to be passed in as a part object, so I simply use part.from_URI to reference this PDF. The MIME type should be application/PDF. The contents of the request include the PDF file and the prompt, and I call model.generate content. Let's see what the model has to say, and it gives me a very nice summary of the scientific paper. That was a dense 8-page research paper, and the model has given me a succinct and concise summary. Now let's try this once again with the same document. My prompt is a little different now. I'm asking the model to play the role of an expert in extracting key insights from documents. I want a clear and concise summary in point form, highlighting main ideas and key details. The rest of the code is the usual boilerplate you're familiar with. This time around, the model gives me a much more detailed summary. The model talks about problem and motivation, approach and methodology, limitations, future work, etc. Let's now work with the second document that I have. This is document 2, and this is a text file. Once again, this is a scientific publication which I downloaded from archive.org. This scientific publication is also based on LLMs, automated literature review using NLP techniques, and LLM-based RAGs. Well, this is the paper. I'm now going to ask the model to compare the two documents we've looked up so far. So let me set up a reference to the PDF file and the text file. And here is my prompt to the model. You're a skilled document analyst. Can you point out 5 differences and 5 commonalities between the documents? The contents now reference 2 documents. We have the PDF file and the text file. The documents are not of the same type, note that. And then of course we have our prompt. Let's see what the model has to say. The 5 differences are based on focus, data source, methodology, evaluation metrics, and output. The 5 commonalities include the use of LLMs, NLP techniques, the data-driven approach, automated analysis, and they both contribute to research. Let's get away from scientific articles for just a bit. Here is an article from the Wall Street Journal that I downloaded in PDF form, and it's a sports-related article. It references a number of personalities and other details in this article. Now, let's ask our model a question about this Wall Street Journal article. Please identify all named entities in this document and explain each of them in a single sentence. Entities can be people, location, organizations. Let's see what the model has to say about this, and it generates a fairly huge response. You can see that a large number of people have been referenced in this article, and you get a quick one-line summary about each person, including the author of this article. And there are some universities and places referenced as well. USC, LSU, Florida State, Jackson State, Oklahoma, Arizona. At the bottom, notice we have a reference to Wolverines, the nickname for the University of Michigan's athletic teams. Next, let's work with this Apache Spark PDF file. This is a document that explains Apache Spark. It's a fairly old document, and I downloaded this from Databricks GitHub site. We are going to be referencing multiple documents, so I'm going to open up the next one. This AI agriculture document is basically a write-up or an article on AI used in agriculture. And this last document that I'm going to use is this document 1 PDF. This is the student sentiment on mental health using LLMs. I'm now going to set the model a simple classification problem. Please classify each of the 4 given documents based on the type of publication. You can see the 4 on lines 5 through 20. We have the Wall Street Journal article, the document explaining Apache Spark, the research paper or the research article on AI agriculture, and document 1 PDF, which is a research paper. The contents list on line 22 contains the 4 PDFs and our prompt. We call model.generate content. Let's see the classification given by the model. You can see the model clearly identifies the news article, the article from the WSJ. I guess that was kind of obvious. A gentle introduction to Apache Spark, a technical book excerpt or a white paper, likely promotional material from Databricks. That was very well identified. Artificial intelligence in the agricultural sector, research article or academic paper likely published in a journal. Again, well identified. And finally, our mental health support sentiment, a research paper or conference proceeding, likely from a computer science or NLP conference. Again, well identified. You can see the model says the archive identifier points towards this being a preprint of a paper submitted to a journal or conference. We'll work with the same 4 PDFs as before, but this time I want the model to output the document name and up to 5 tags that the model might associate with each document. Let's see what kinds of tags the model generates. The Wall Street Journal article has college football, Travis Hunter, Heisman Trophy. This sounds good. The Apache Spark tags seem spot on as well. And then we have the right tags for AI in agriculture. But for the 4th document, sentiment analysis of mental health systems, there seem to be no tags at all. Now, I should tell you that I ran this multiple times, and each time there were no tags for the 4th document. No errors were logged with the model. Maybe it just found it hard to generate tags for that particular document. I'm not really sure. Now, let's open up this last PDF here, AI in Healthcare. And this again seems to be a research paper that talks about the applications of artificial intelligence in healthcare. Let's get a quick sense of what this paper is about using the Gemini model. Please summarize this document in 4 or 5 lines. That's my prompt to the Gemini model. And the model gives me a very helpful, concise, and easy to read summary. Now we have the AI agriculture document that we looked at earlier. I have some specific questions about that document. You can see my questions on lines 3 through 5. What areas of agriculture can AI be used? How much money could be saved using AI in agriculture? What are some concerns? Let's see what the model has to say about all of this, and here is the model's response. You can see the response has been broken down by question. In response to question 2, I like that the model clearly says that the document doesn't provide a specific dollar figure for the potential savings, which is great. The paper indeed does not provide a dollar figure. Just like with images, you can ask the model to compare two documents. I've passed the model the AI in agriculture and AI in healthcare documents. My prompt says, please identify common points regarding AI use in both industries. Please also identify points that are diametrically opposite in each industry. And here's what the model has to say. What's common is both are data-driven, they use predictive modeling and automation and some others. Diametrically opposite, regulation and ethical considerations are more important in healthcare. Data sensitivity and time sensitivity are more important in healthcare. Let's see how good the model is at identifying PII or personally identifiable information. I pass in document 1, which is the research paper on mental health systems. The model very clearly tells me that there is no PII in this document. The author's affiliations are listed, but this is not considered PII. Let's ask the model the exact same question about personally identifiable information, but I pass in the Wall Street Journal article. And once again, the model says there is no PII present in this document. Even though the article is on Travis Hunter, he's a public figure and it focuses on his athletic achievements, not on personal information. I do have a document here with personal sensitive information. Let me open this up so that we can take a look. Notice that this contains names, addresses, phone numbers, and relationships. So clearly a lot of PII. Let's see what the model has to say about this. Please identify any instances of PII in this document. And notice that the model identifies all of the personal information that this document contains. Maybe you'd like this information in the JSON format. Please extract the information and give it to me in the JSON format. For example, name followed by a list of names. Let's see what the model has to say. Notice it gives me all of the different personal information in the JSON format. There are multiple names, multiple dates of birth, multiple email addresses and phone numbers, all in a nice structured format. Gemini's document understanding capabilities are very powerful. And in this demo, you've seen some of the different ways in which we can leverage document understanding. In this demo, we'll see how you can use the Imagine model on Vertex AI for image generation. The Imagine model is very powerful and allows you to perform a number of different tasks with images. You can generate novel images with a text prompt. We'll see that. That is text to image AI generation. You can edit an entire image or a part of an image using a text prompt without using a mask for that specific portion of the image. You can upscale images, or you can use your images of a concept, either subject or style, to customize image generation, preserving the appearance of a person, product, or a pet. At the time of this recording, all of these features were not generally available. You had to explicitly get approval from Google to use many of these image generation features. So I'll show you what's freely available and that you should be able to work with. But it's quite possible that by the time you're watching this course, there'll be many more features available on Imagine. I'm going to use the Matplotlib library to display images in a grid. So I'm going to go ahead and pip install Matplotlib within my virtual environment. We may need the pillow library as well, so I'm going to go ahead and install this. This is already available within my virtual environment, and you'll see that message. Let's set up the imports that we need and initialize our Python client by invoking vertexai.init. The latest version of the Imagine 3 model at the time of this recording happens to be Imagine 3.0 generate 001. It's quite possible that newer models will be available soon, so you should just make use of the latest model. Instantiating a reference to this model is a little different. We call image generation model dot from pretrained to load this model into our notebook. Now let's send our first text prompt to generate an image. I'd like to see a cartoon raccoon wearing glasses reading a book by a cozy fireplace. I call generate images and pass in this prompt. By default, the model will generate a single image. I access that image by indexing into the images property of the response and call show in order to display the image. And here is our cartoon raccoon reading a book by a cozy fireplace. Now I'm going to soon generate multiple images and I'll show you how you can do it. In order to display those images in a little grid, I'm going to make use of Matplotlib. Here is a helper function, display images in grid, that takes in a list of images as an input argument. We then compute the number of rows in the grid based on how many images we are going to display. We'll have a maximum of 4 images in each row. N calls is the minimum of the length of images plus 1 or 4. The rest of the code on lines 10 through 25 sets up a matplotlib figure and axis and then displays the individual images in a grid format. Observe on line 14, we access the pillow image associated with each image object in the response using ._pil_image. Now let's send a prompt to this image generation model. A vibrant Greek salad with feta cheese, olives, cucumber, and tomatoes. I call model.generateImages with the prompt and I've passed in a number of images equal to 4. And I get the images in the response and pass them into display images in grid. And here are the 4 images of the Greek salad that we requested. I must admit, they look delicious. All generative models have an element of probability associated with their output. Now, using the same prompt as before, I'm going to call generate images and display the images in the grid. And this time around, notice that the salad images are different from the salad images that we got previously. The ingredients are the same. You can see the tomatoes, the cucumbers, and the feta cheese. But each salad image is very different from the previously generated images. Let's say you want to be able to generate images in a reproducible manner. You can make use of the seed parameter. Here I call generate images on the model, specify the same prompt number of images 4, but I set the seed to a specific value 42. In order to be able to set the seed parameter, you need to set add watermark to false. Otherwise, the seed parameter will not be considered. The seed parameter is used to initialize the random number generator in processes like image generation, ensuring that the same sequence of random numbers is used every time the process is run. This is what allows us to generate reproducible images. Now, here are the images generated when the seed is set to 42. Note that the first image has a triangular shaped feta cheese block. Now keep this in mind, and I'm going to use the same seed with the same prompt to generate images. Look at the generate images function, same prompt, same number of images, same seed 42, add watermark is false, and here is the result from the model. The first image has the triangular feta cheese, and in fact, you can compare every image here in the output, and they're very similar to the previously generated images. When you compare them, you can see the images are not identical, but they are very, very similar, and some of them are identical. Imagine allows you to specify negative prompts as well, though I've found that this doesn't always work that well. The only new parameter I pass to the model here in this code is on line 5, negative prompt, no lettuce, no cut onions. So I still have the same prompt. So I still want my Greek salad with feta cheese, but I don't want lettuce and I don't want cut onions. Let's look at the images. I feel that the lettuce content is definitely reduced, but there are still cut onions visible. So you can specify negative prompts. In practice, I found these don't work as well as the positive prompts that you pass in. By default, the aspect ratio of the generated images, that is the ratio of the width to height of the image, is 1:1. But you can specify a different aspect ratio if you want to. Here I have a prompt for a juicy, perfectly grilled beef patty layered with melted cheddar cheese. When I call generate images, I pass in the aspect ratio of the image that I want generated, 4:3. The image generated will be in landscape mode. Let's go ahead and run this. And here is our juicy burger. And you can see that the image is much broader than its tall in landscape mode. The Imagine model generates highly photorealistic images. And you can see that this is borne out by the image on screen. That burger definitely looks very real. Let's try a slightly different aspect ratio. Here I want an image of a weathered lighthouse perched on jagged cliffs. And then I have some more details in my prompt. The lighthouse has peeling paint, broken glass, and there are dramatic crashing waves below. I call model.generate images. I specify the aspect ratio as 16:9. And here is the resulting image, and you have to admit it's pretty fantastic. Look at the waves, the greenery, and the lighthouse. The model has included the peeling paint on the lighthouse as well. You can also specify safety filter settings when you're generating images. These parameters control for the safety and appropriateness of the generated image. You'll find though that in general, the models have been trained pretty rigorously to not generate unsafe images. So it's hard for me to demonstrate this with a jailbreaking prompt. Here I've specified my safety filter level as block low and above. This is the strongest filtering level, the most strict blocking. Other possible values include block medium and above, block only high, or block none. I've asked Imagine to show an empty train platform with an old steam engine billowing clouds of smoke. And here is the pretty amazing photorealistic image. The Imagine model can generate very realistic looking people, but you need special approval from Google in order to use that feature, at least at the time of this recording. Here I ask for a train platform in India with shops and people hurrying about. In order to be able to generate images of people, you have to set the person generation parameter. You can see that on line 10. Possible values include don't allow, allow adult, and allow all. Now I've set allow adult, but you'll see that when I run this code, I immediately encounter an error because Google hasn't given me the permissions to use person generation for images. You can see that setting person generation is currently an allow list only feature. Now, let's say I wanted to generate images that were considered harmful. I could turn the safety filter level off. And that's exactly what I've done here in this example. On line 9, notice my safety filter level is set to block none. And when I run this, I again encounter an error. And the reason for that is, well, you can't turn off safety settings. That's an allow list only feature yet again. The block none safety setting is currently an allow list only feature. You can see because of the photorealistic images that Imagine generates, Google is very careful about who can do what at these very early stages. You can save out the image responses from your model to a file on your local machine. Let's see an example of that. Here is my prompt, a close-up shot of coffee beans scattered on a wooden table in a rustic kitchen, and the output file is coffeebeans.png. This is where I want to save out the resulting image. As usual, I make a request to the image generation model. I call generation model.generateImages, pass in the prompt, number of images is 1, aspect ratio 16:9, and I've set add watermark to true. Imagine will generate an image with a digital watermark. Watermarks are used to indicate ownership, protect intellectual property, or deter unauthorized use of images. A digital watermark is like an invisible signature embedded within the image data itself, so you won't be able to visibly see the watermark. Once we get the response from the model on line 8, I call the save method on the response, specify the location to save to our output file, and you can choose to include the generation parameters if you want to. I've just set include generation parameters to false. On line 10, I display the images, and on line 12, I print out the size of the output image in bytes. Here is our image of coffee beans. I must say it looks quite delicious. And let's scroll down and see the length of the output image, and you can see it's about 1,000,000 bytes. Now, this image should have been saved in our current working directory as coffeebeans.png, and you can see it right there. You can double click on this image and view this image and confirm that it is indeed the same coffee bean image, and it is. A digital watermark has been added to this image, and you can actually get the Imagine model to verify digital watermarks. The Imagine model will be able to identify and accept images that it has generated, and it will reject those images that have been generated by other sites and which have embedded watermarks. Let's try reading in our coffee beans PNG file and see whether Imagine is able to identify this as a file that it has generated. I specify the input file on line 6. On lines 8 through 10, I read in the watermark verification model. This is the image verification at 001 model. On line 11, we load the image from the file using the pillow library. And then on line 13, we call verification model.verifyImage. This will give us a watermark verification response, and on lines 15 through 17, we'll print out the watermark verification result. When you run this for the coffee beans image, you can see that the watermark verification result was accept. Thanks to the digital watermark, Imagine correctly identified this image as one that it generated. Now, if you pick an image from a different source that does not contain Imagine's digital watermark, well, Imagine will reject that image. Here in the images folder, I have an image called cat.jpg that I downloaded from pexels.com. This image will clearly not have Imagine's digital watermark. So let's head back to our notebook and try and verify this image. The input file is images/cat.jpg. We load in the watermark verification model. I call image.load from file to load in the image. We call verification model.verifyImage and print out the watermark verification result. And for this image, well, it does not contain the digital watermark that Imagine adds to its images, and you can see that the result says reject. The Imagine model understands a variety of other languages as well. Here is a prompt that I have in Hindi. I'm asking the model to generate an image that is a poster with adventure awaits. When I call generate images, I pass in the prompt, specify the language as Hindi, HI is the code, and an aspect ratio of 16:9. And here is the generated image. Let's try a prompt in Spanish. This prompt asks the model to generate Tokyo at night with neon lights, a wide angle lens, and it should be a street photographed. I call generate images with the language parameter set to ES. And here is what the result is: a pretty good photograph. The model clearly understands Spanish as well. What I've noticed is if you ask the model to generate images that include text, it doesn't do very well. Provide a menu for an Italian restaurant, give each menu item a brief description. And here you can see the result. There is a menu, but the text there is basically gibberish. Let's try this once again with a clearer text prompt. Provide an image of the maths equation for calculating option delta. And you can see that it generates pretty much a rubbish equation. The image generation model is not great at generating text embedded within images. But you can always style the text generated in images. Provide an image of a modern art depicting the formula of an options delta. And this will give you something that's interesting and pretty surreal. Talking of surreal, here is another prompt. Generate a surrealist map of Europe. And the model does pretty well on this. But remember, you cannot generate people without prior approval.